Hello, welcome to Chapter 6. It is titled Congruence, and I just want to let you know this is where we actually start writing our own proofs. In your book, the Chapter 6 starts on page 206. There's a picture of a Chinese checkerboard. It doesn't look like this one. It's a little bit fancier with colors, but you get the basic idea. I'm pretty sure everybody in the class has played this game at one time or another, but it's actually, this game is not from China, and it's obviously not checkers, okay? The book will tell you more about that on page 207, but the reason why I went ahead and included a picture is because it actually displays various congruent figures. Okay, this game itself illustrates proofs. It's a strategy, okay, like chess and checkers. It actually requires deductive thinking. So, for instance, a modus tollens argument occurs when you decide against a certain move. If I move here, then he will move there. So from there, he could triple jump me. Therefore, I will not move there. So you've been doing this kind of reasoning for a long time. You just didn't have a name to it. Okay, so let's get started on section 6.1. It's called Congruent Segments. Okay, so there's some general things that we need to talk about before we jump into writing our first proofs. Okay, first, there is no set way of proving theorems. Alright, we've talked about inductive and deductive, and even within one or the other, there's different ways of approaching it. But there are patterns of reasoning, and you need to follow those. So I'm going to give you some general hints. They're in your book, but they're all very good. So I just want you to keep them in mind as you put together a proof. Also keep in mind that they're like a puzzle. So when we show you proofs in the book, in the textbook we're looking at, they're perfect. They're perfect proofs. And the reason is because mathematicians have been doing them for so long that they have shortened them. There's no extra steps. There's no extra words even. I mean, they're as short and concise as possible. So if you write a proof and it is a little bit longer, you have some extra steps, it's not wrong. It just, if you got there with the same steps included, then you got the proof right. So I don't want you to get really hung up on, my proof doesn't look like Mrs. Kirk's proof. Okay, this is a puzzle, and like some people put together the puzzle by putting the whole frame and doing all the edge pieces first. Some people put together puzzles by doing all the same color, like they'll look at all the purple pieces, then they'll put together all the red, and then they'll see what's colors in between that they can hook. So, okay, you have to get a little bit, you don't have to think like I think, I guess is the bottom line. So let's go ahead and talk about some of these hints. The first is identify the premise, which is going to be what's given. So it'll just be a statement, and you kind of want to break it down. You also want to see where you're going, okay? That the conclusion is what you want your last statement to be. And so what you start with and where you end with, you have to kind of determine how can I get to that place? Just like when you're driving a car, when you start at your house, when you're going to Cleveland, you need to know what route you're going to take. Okay, so you also might want to draw a picture. You don't have to draw a picture, but if you don't, sometimes it's hard to think about what they're actually saying. You also want to write down definitions, postulates, anything that you've already proved, so you can look at the steps it took to prove previous things. So, as in today, when we write our first proofs, you want to keep those. Alright, keep those in your notes so you can go back and look at them as we go and get to more complicated proofs. And also, working backwards is very helpful. Starting where you need to end and going backwards to see if you can end with what you started with. It's very possible. Remember, to prove a theorem, you can only use definitions and postulates and previously proved theorems. So, like I said, once we have a foundation, theorems get easier to prove because we can use other theorems. But when we're just starting here in section 1, we're going to pretend we don't know any theorems. We haven't proven any of them. I've told you several, but we haven't proven them. So we're going to use deductive reasoning to derive a conclusion. Okay, so like I said, there's at least 2 kinds of proofs. I would say there's more, but the deductive type, which we're going to use law of deduction, and then there's the 2-column proof. Now these are all deductive proofs. We're not even talking about inductive proofs at all, so that's why there's more than 2 in my opinion. But law of deduction proofs are going to be like on page 209. So if you open your textbook, this is where you would be using maybe some pictures. You don't have a 2-column setup, which is what we're going to do pretty much all the time. We're going to do a 2-column proof. So like I said, on page 209, the prove a line and a point not on that line are contained in one and only one plane. Okay, so this is theorem 1.2 and it's asking us to prove it. Well, we don't have a given, right? We just have to talk about lines and a point that would be not on the line, a point that would be on the line. A given would be there is a line and then there is a point that's on that line, because that's part of what we're trying to prove. We have to do a little assuming. And you know, although it is an example in your book, I'm not going to ask you to do a proof like this, so I just want you to know that it exists. Alright, but example 2, we are going to do proofs like this. This is a pretty concise proof. There are actually ones that are shorter, but this has 5 statements and 5 reasons. This is the shortest. Now, like I said, if you come up with a few more as you're thinking through proofs, don't get panicky about it. Okay, so a line and a point not on that line are contained in one and only one plane. So the given is line L, a point K that's not on line L, and we need to prove a plane P containing line L and point K. So here's my 2 columns. I'm going to have statements and reasons. I typically, when I'm doing this by hand, I write a line. I just draw a line to separate the 2 columns and then make like a T-chart. Okay, so our first is always going to be our given. There is a line L and a point K not on the line. Okay, so that's given. Now, the next thing we have to talk about is that line L has points, right? It has infinitely many, but we're just going to talk about 2 points, and that is from the expansion postulate. Now, you notice there's some abbreviation postulate there. I also will abbreviate definition DEF, or you can abbreviate it DEFN. Theorem, TH or THM. Sometimes I put THER, which really isn't proper, but I don't know why, but my geometry teacher taught me that, so I haven't ever really fixed it. Property, PROP. Addition, I typically write the plus sign, but you can also just write add. And then multiplication, MULT. I don't use an X because that can get confusing. It's a letter. Equality, you can use an equal sign. Congruent, you can use the congruent sign. Triangle, instead of writing out the word triangle, you just draw a triangle. Perpendicular we've talked about, and parallel we've talked about, and angle we've talked about. So you can use the symbolic math symbols to abbreviate words. So, okay, all that to say, now, here we are. We know we have a line that contains 2 points. We know that that line does not contain point K, and now we need to talk about how these points, X and Y and K, are non-collinear. The only way we can talk about that is by the definition of non-collinear. Okay, so now we know K does not lie on line L. It is not anywhere on the same line with X and Y. Now we have to talk about that they lie on the same plane. Okay, so points X, Y, and K all are on one plane. And if you look back, that is our plane postulate. Okay, we actually know a postulate that says that. And then we're done. Line L and point K are on plane P, and that is the flat plane postulate. So that's your whole proof right there. You have now step by step proven the flat plane postulate. Okay, so here's our first theorem we need to talk about. There is a proof for this in your textbook as well. It's called the congruent segment bisector theorem. If two congruent segments are bisected, then the four resulting segments are congruent. Okay, so think about that for a second. A picture would be two segments, and then they're bisected, so now you have four segments. And they're all going to be congruent because those segments started off being congruent. And then the next theorem is the segment congruence is an equivalence relation. Remember, equivalent relations have three properties. Okay, so remember the reflexive property of congruent segments, symmetric, and transitive. So segment congruence is an equivalence relation. So if you know that segments are congruent, we can use all three of those properties however we might need them. They're just extra puzzle pieces we might need. So I do want you to review the proof on page 211. You don't have to write it down in your notes because it's already in your book, but I do want you to know that it exists. It's a little bit more complicated because it talks about the midpoint theorem, and we're not quite up to that ability to write out this proof yet, so I didn't want to freak you out too bad. I'm going to give you a whisk summary on the next slide. Okay, so here are four statements, and I want you to draw conclusions from them. So I gave you a statement, and maybe you can tell me what you know about that statement. Okay, it's not necessarily a theorem or a postulate. It's just something that you already know. It might be a definition. It might just be a conclusion you can draw. So I want you to write me a sentence for each one of these on for a conclusion, and email those to me, and I will see you in class.